so I think we're ready to start, even though the clicker might not be working, but I can work around that. So yeah, I'm really happy to talk with you guys. First of all, like, who had a great week here at CppCon? Like, please raise your hands. And I will look very closely. If I see one hand not raised, I'm going to talk with him after. So yeah, I was very happy to talk with a lot of you guys about performance, profiling, the stuff I spent most of my time on last year. And it was really interesting to see that many of you shared the same pain points which I had about this topic. So the whole journey started around like 1 year ago, when I was sitting in my office in Germany, based in Karlsruhe. I was working on like huge C++ project, and like always the question was, well, can you make this run faster? I was thinking like, well, I can try, so let's see. And I was sitting there using the tools I've always been using the same techniques I've been using for years and years, and I always like kept thinking to myself, well, there had to be something a bit easier to do this problem. And so I came across this, now I probably know why the clicker was not working, perfect. So I came across this quote from Donald Knuth, which I think fits quite well to the theme of this talk. Programmers waste enormous amounts of time thinking about or worrying about the speeds of non-critical parts of their program. Originally, it was in a different context, I admit. It was about like premature optimization. But nonetheless, I still think it fits quite nicely, because I sort of like to rephrase it. To make things go fast, you need to figure out what's slow. That's basically like the core thing about profiling, like performance tracking, all that sort of stuff. We want to find out what's slow so we can make it faster. So let's have a look. Like, there are tools out there, right? For sure. And yes, there are many. I listed some of maybe the most known there. This list is by far not complete. So we have like benchmarking libraries, we have profilers, we have tools which are closer to hardware and give you like more hardware information. And all those tools are great. That's really important for me to say. Like, I don't think any of those tools are like worse than what we build. Not at all. It's not a competition. But like each of those tools, they solved a set of problems, but it wasn't quite a set we had, like the problems we had. So we needed something a bit different. But first, let's have a brief look like how they work generally, like those tools. So we have like 3 different types to make it a bit easier. We have sample-based profiling. So that basically is, while your program is running, from the outside, you go and check like where the program is currently at. And then you record that. And you do that over and over and over again. And then by that, you have the collection. So what's good about it, you don't have to change your program, right? So that's good. So we have generally like lower overhead. But the accuracy is the problem. Because the more often you check per second, then you increase like the overhead. And the less often you check, then you have like lower accuracy. So that's the problem. Then you have the instrumentation-based profiling. That's basically you change something in your source code. Like, for example, at the start of the function, you say, well, starting record here. And at the end, we say, well, this is now the end of the function. And we collect those traces of the program execution. This is like really good because it has like high accuracy. But the problem is you add overhead to your program, right? And that's the downside of it. And also, there's micro-benchmarking. So micro-benchmarking is basically like a controlled experiment. So you measure a single function or a specific part of your program, and usually it runs this function in a loop, but we'll get to that in a second. Before we dive deeper into the problem, I want you to have a really quick look at this function. So this is a very important function. What we do is that we say start, we measure the time, then we simulate some work. Most important work is sleep, so we sleep. Then we measure the end of this function, and we know the duration. And I want to know, like, who of you guys wrote something like this or similar like this? Doesn't matter if it's like chrono or another timestamp. Like, who wrote such a kind of manual timestamping? So yeah, that's like 95%, I think. And I did too. I did so many times. And also when I was using those tools, I went back to like manual timing more often than I would like to admit, I guess. So let's think about what we need in practice. Let's imagine we had like a whiteboard and can really choose like what are the properties we would have from such a performance benchmarking, however you want to call it, tool to help us find slow parts in our program. And there are many things like coming to mind, like directly, like it should be fast, it should be accurate, it should be free, it should be easy to use, like all that stuff. But I thought, well, we need to sort of like present it in a more like simple way, like not just listing all those properties, but really go through them, because I think it's important to understand those pain points. And if we invert this question, in a sense, this is also why this is hard. Because each of the tools you saw at the previous slide, they solve some of those problems, but like not all of them. So I'm going to use those terms like interchangeable. I'm going to sometimes talk about properties, which I would like from such tools, and sometimes like what is the challenge, but at the end of the day, it's the same technical question. So let's go through them. One problem we face is that we have to integrate such tools into legacy code or existing code bases, right? So for example, let's look at a nano benchmark library, but all those micro benchmark code looks more or less the same. So you write a simple function, you define some properties, like how often should it run, maybe like do not optimize away, please, compiler, stuff like that. And then you call your actual function you want to measure, it loops that, it calls it over and over again, and you get the results. So of course it has its like upsides, you get like a lot of statistical insights, but it also has its downsides. Often our legacy code bases look a bit more like this picture on the right. So you can't just extract like every important part of the program and like call it directly, since stuff interferes. Then micro benchmarks, they also have pitfalls. You heard like at Monday, I think, at one of the first talks, a great talk about exactly that topic. Then also what's very important, the behavior might change. So if you have a like specific piece of code and you run it in a micro benchmark and you optimize it and you're like very happy, like nice, it's working great. And later you put it in your like big production code, it might behave completely different. And that's something which is very annoying. So yeah, that's hard. And also one minor thing, I also would like to be able to measure like part of functions, because sometimes we go into a code base, we have like a function which is like 200 lines, and like, oh God, why? But it is what it is. But maybe I just want to measure like the middle part of the function, because it's like some startup at the beginning and some logging at the end, but I really just care about the middle part. So going further on this topic of I want to integrate such a tool in existing code base, we have more challenges. Like I want minimal build system impact, right? Doesn't matter if it uses like CMake or any package manager or whatever, it should be very easy to introduce it into my build system. And that more or less by definition also means such a tool should have like 0 or minimal dependencies, right? Because the more dependencies you add complexity to your code. And if you want to make things go fast, adding complexity is like the last thing you want. Then also you need broad compiler capability, because when I'm thinking of such a tool, I want to use it like on every project and not be like, well, now I can use it for my Windows project, but not for my like Linux project or something like that, or GCC compiler and so on. So that's really important that such a tool should support all the major compilers. Then the next is probably a hot topic, like with older C++ standard, like how old should the code base be? The tool should still support. And there is probably a compromise, because with newer code base you can make maybe cooler stuff, but then you support less code. So that's also something you have to keep in mind. And lastly, it should change as little code as possible. Some tools, like we saw the sample base, they don't need to change code at all, so that's neat. But if it changes code, it should be like really minimal, because else you're adding complexity again, and you also have this problem with development and production, and that's precisely the point I'm coming to next. I would like to be able to use the same tool doing development and production. What it means is I'm thinking about like 2 topics. First is about like the compiler flags. So let's say I run my program in debug or in release, it should still work. Like it should not optimize away, or like my profiling tool give me information which is then not matching the release code. So that's not something which I want. But also I want to control precisely what's tracked. For example, in production, when I want to have this tool running, I might want to track like some major function, like the big functions, just to see is the system like generally behaving well. But during development, I might want to track like everything, so to get the minor details and stuff like that. So yeah, if I have a wish, I would like to have a tool which works on both, doing development and production. There are some more specific needs which I would like to have in production. Like I would like maybe to export the results, do some logging, some database, and whatever, so I can like collect the data over time. Of course, the most important thing, it should have very low overhead, because when it's enabled in production, well, it slows down the production system. So we need to have this effect as low as possible. Then stability is another thing, right? We should handle millions and millions of events. What we did so often is, even during development, we had some like huge code base, again, sadly, and collected the events, for example, Visual Studio Performance Profiler, and had like 100 billion events. And then you load that into your debug analysis, and it like takes ages. Sometimes it crashes. It's just not fun to work with. So it really needs to be like stable also with those events. And that's also important. There are scenarios where like every milli or nanosecond matters, right? I'm sure you've seen the talks. So it needs to be disabled like very easily. So let's say I want to have some sort of guarantee that if I disable it, my program behaves exactly as if such a tool wouldn't be integrated at all. All right. Then also it should be customizable. Because like for some use cases, we have like specific metrics we want to talk about, right? So there might be hardware related or specific domain knowledge where I know like, oh, this is very important for me. And also that means I want to be able to access the results in code because we're all coders after all. And if I get like the result not just in some file, I get it directly in a code, I can do more with it. And I also want to be able to define like custom workflows. Maybe I don't want to start measure like the first 1 minute of my program. Maybe I want to measure like the results every hour and then dump them away or stuff like that. So I want to be able to like customize it to my needs, basically. All right, and now the last thing, which probably is the most important, the insights such a tool has to generate. So as I mentioned at the beginning, we want to find out what's slow, right? So we need to find out where are the performance bottlenecks, and even like in complex multi-threaded scenarios. Like I can imagine we run this tool and it's like, well, this is a function you need to look. That would be the dream scenario, basically. Also, there is other stuff like outlier detection. Let's say we have a function which is like fast most of the time, but sometimes it takes ages. So I would like to detect that. Then precision, precision in the sense of like the insight it generates, like where is actually the stuff happening. So what we have quite a lot, especially like with our junior programmers, if they use those tools, they get like those huge stack traces, and some is then in the kernel and some is somewhere else. I think some of you also saw it in the talk some hours ago, where we have like, well, this code is now spent in malloc and not actually in the constructor because it's optimized away and that sort of stuff. So we really want to know like, well, where is the time actually spent? We want to know basic stuff like how often is a function called, how many threads did call a function, for example, how much impact has this specific function on my overall performance. And also, if we don't track everything, we want to know like how much of our total runtime did we track, right? Because we often tend to have like a wrong gut feeling. Let's say I measure part of the program and I'm really focusing on that, and at the end it turns out, well, actually the whole measurement process only covered like 20% of the whole runtime, and like the actual bottleneck is somewhere else. So I would like to have this information, like how much of the total runtime did I actually track. And I want to have like as much information as possible with as little overhead as possible. Of course, this is kind of like conflicting, but the more information I get, the more I know about those bottlenecks. Like I want like statistical stuff. We're gonna get into that in a minute. Like not just like it took 2 minutes. I want to get more and more details, and that should enable us to do like data-driven decisions. So right, so it's not just like I measure once on one system and I do anything. Like we want to be sure that when we optimize something, it carries over like on our other systems, in our production code, stuff like that. And last but not least, that all should also work like in multi-threaded scenarios where we have like loads of different threads interacting with each other, and yeah, making that stuff usually way more complete. So yeah, those were exactly the pain points we had. So we built Ctrack basically to solve that subset for ourselves. Again, this list of problems I presented, there is not like complete. There might be other problems or other priorities you guys have, and then probably it's not a tool to solve all of them. But those pain points were quite frequent. So I saw them reoccurring quite a lot, and so I thought, well, this is probably a nice list of what such a tool should solve. So I'm not going to get into that too much, but basically Ctrack is an open source library. It's completely open source. It's MIT licensed, completely free. It supports all major compilers. It compiles without warnings. Now by the community, it has already been integrated in various like package managers, but basically, yeah, you can use it as a single header library. You can use it via CMake. It's very easy to integrate. And the standard we have is like, we can use C++17 or newer projects. All right. Now let's spend a minute to think about the Ctrack like design philosophies, because like the one pain point we have is the overhead, right? That's like very crucial. So our priority doing Ctrack is, well, during runtime, the overhead has to be as low as possible. That's like highest priority. And so the recording speed is like priority number 1. And then doing like the analysis, like the calculation of the result, that can take some more time. So at the end, because like it's always a trade-off, right? So if you calculate more doing the recording, well, you save some time at the end, but it slows down your code more. So yeah, just to keep that in mind, we're gonna get closer to that in a minute. But yeah, that's the general idea behind that. But first, let's have a look like how would we integrate in a code base. Going back to our very, very important function, this is how I timed it manually, and timing it using Ctrack looks like this. So basically, we have this one macro, which we write at the start of a scope or a function in this case, and that's it. The whole function will be tracked. And again, I'm going to explain later how exactly that works. But yeah, it's quite nice because even if I manually just, let's say I have a code base, I don't want to track everything, but I want to track like one function or something specific. For me nowadays, it's even faster to just include Ctrack, do this macro, and I have the results, like all I need, instead of like starting to manually time stuff. And that was for us really like let's say like a benchmark, since our developers started to using like this more, even like on fresh, like small project, like some script, whatever. Yeah, it's kind of like a good validation that it's easy to use. All right, how does it look at the end? So you have this Ctrack call, and at the end, somewhere in the program, you can call print, or there are also some other options, and you get those tables, and you get them, like you can have them in your terminal, you can have them with colors, without colors, you can have them in a string. There are many ways to export them. For the slide, since like this is probably hard to read, I converted them into slide-compatible views. So let's start first with our like overview table, because Ctrack gives you two kinds of tables as output. The overview table is generally solving the problem, like where do I need to look more exactly? So this gives you like all the functions and a bit more stuff. So let's go through it. We have like start and end. So when did our program start up and when it stopped? How much running time is our program in total? How much of the time was spent in Ctrack? And also like how much percent did we spend in Ctrack? And then we have like this overview table where all the functions are listed. In this case, we just had one Ctrack call, so it's just one entry, where we see the file name, the function, the line, how many times it was called, and some more metrics on the columns besides that. So let's look a bit into them. I want to explain them with an example because I think that's easiest to like visualize what I want to show on this like main overview table. So let's say we have those two functions. We have a slow function waiting for 900 milliseconds. Eternity is super slow. Okay, slow function. And then we have this fast function. The function itself is much faster, just waiting 100 milliseconds, but it's calling the slow function, right? So those are the two functions we're going to talk about. In this first metric called time active, that's basically defining from a top-down view, like how long did those functions take? And yeah, well, if we just go through the program flow, starting with this, with the inner function, the slow function, well, that took 900 milliseconds, doesn't call anything else. The whole program runs for 1 second, so it's active 90% of the time. All right, the fast function, well, it itself should be faster, but since it's calling a child, well, it's like having its own time and the time of its child. So the time active is like the whole second and also for the whole program. So sometimes this is nice to have because you want to know, like from a like just top-down perspective, like where should I start and go this way. But sometimes you just also want to spot like the bottlenecks more or less instantly. So what we need to do that is that we have another metric called time active exclusive. And what this basically does is that we exclude all childs of functions which are also tracked from this main function. So we have the same two functions, obviously. But this metric now gives us a different result. For the slow function, it doesn't change anything. It's still 900 milliseconds. It's still 90% of the total runtime of this program, which is 1 second. But for the fast function, it changes completely, right? Because the time spent exclusive in the fast function is now just 100 milliseconds, or 10% of the total time. So those are the two metrics we show on the main table. So you can find out very quickly which are the functions I need to look at closer. Yeah, I also, like, I think you guys probably understand, but I just thought, well, why not visualize it? So let's loop through it one more time, since we're using this concept quite a lot during this talk. So if you have like those two functions running, like from a top-down view, we have like starting the slow function, it's gonna call the fast function, sometimes it returns, and then we're back. So the time active, inclusive if you want, is like the whole block. And the time active exclusive is then just calculating the part which is actually spent like in one function or the other. All right, and then the last thing is it also needs to work with multiple threads. So we have like a very simple threading example. the top two functions are the same which we had already. It's just setting some like atomic bool to being ready. And then we have another function at the bottom, which just waits all the time, busy waits. Let's generate some CPU load until this bool is set, and then it exits. And yeah, well, if we look at the result, it's precisely what we would expect. We're gonna look at many, many more of those tables, so I'm gonna take this like very short. But we see those three functions we tracked. We see the waiting thread was active pretty much the whole time, right? That's what we would expect since, well, it started, it waited until everything else finishes, and then it could finish. But then we also had the two other functions from the other thread. And yeah, you can see there, this 900 millisecond function took like 90%, no? Give or take. It's a bit, it's not perfect, right? I've been running this on Windows after all, so we have some variants. And the worker thread with the 100 milliseconds was around like 10%. All right. So then the last thing we have in this main table is that we have those ranges. I think if you look there, like you see a number, like it's not always for the full range. So what does it mean? This is an idea we stole from game benchmarks or system benchmarks, for example. Often, you don't care about like what's the fastest event or whatever. You want to know like generally like a normal event, like how fast is it? So that's why excluding outliers is quite nice. So we can use that to like mitigate system noise. Like sometimes we might have like a cache miss, which is like very, very rare, and we don't want to care about it. Or we have like the first call of a function has some like startup or whatever, and we don't want to know about it. Or maybe like we get a null input and can return instantly, but it's also not typical for our function. So we can mitigate stuff like that. Also, we can mitigate like typical system noise because there's load in our system, right? Other processes going on. So we have like typical some variants, and the events in the middle are probably the ones which tell you the best story about like your true algorithmic costs of your functions. And yeah, this basically is all about that we know what's the real like hot path performance of this function. And just as a note, of course, this range can be custom. So as a default, we have this like 1% outlier on both sides. Works quite nice, but you can adjust it to your needs as you wish. All right. So looking now at the second type of function we have, going back to the first example, those are the details tables. So for each function, we have these two small tables. First of all, again, what function it is, where it is. Then we have the time accumulation. So like a total runtime, if you all add it up, how much did it take? It's different from the time active because let's say we have one function which gets called like from 4 threads at the same time, it takes 1 second. It would in total take 4 seconds like added time, but like top-down view, it's just 1 second, right? So we sometimes want both information, so we have that there. And then for the other information, I'm gonna go through this by a list because it's a bit easier than a table. We also see how many threads did call this function, which is quite nice. We have the standard deviation for the variance of the function. It's also very important to know, like how much does my function like vary or fluctuate. And then we have the CV. This is sort of like a normalized version of the standard deviation because let's say a function fluctuates between 1 millisecond and 100. It has much more variance than a function which would take like, well, I don't know, 10 minutes or 9 minutes, but this gets rid of this factor. So you can like compare them without the unit. And then for those 3 groups we just discussed, like for our fastest, for our center events, and for the slowest events, we have those like minimum, like the fastest in the fastest, medium, and max. So we have like all sorts of those data and also the average. So we get all basically all entries we need. That's what you see on this table. So we start with the fast group, so like the fastest took like this, and so on. And in this case, since we just called the function one time, we don't have a fastest and the slowest group. It's just the center group. But we get more samples in a second. All right, now let's talk a bit about accuracy, because comparing with a sample-based profiler, which like something which is really easy to use, right, which many people use, we designed like a small example to a bit of show or visualize the problems which you might have with sample profilers. So one thing is that we have like a micro operation, which is like super fast, and then we have a function with like high variance. So we have a function, when it gets a true parameter, it will sleep 100 milliseconds, else just 1, right? By nature, this function has quite high variance. All right, so then we write a small program calling those. So we call the micro operation 1,000 times, and the other function, the variable function, we call it 100 times. So what time should we expect? Well, around 1 second each. Well, it's a bit because we call 1,000 times 1 millisecond, right? So it's 1 second there. And also for the other function, it's basically 1 second and some more milliseconds, but yeah, give or take. What happens if we run this in a sample-based profiler? Well, it shows us, in this case, in the first run, the micro-operation 53%, which is sort of fine, but then it showed us 10% the variable timing function, because it missed it sometimes. And then it said, yeah, well, we spend it in this kernel function. But that's not the main point I want to talk about, because the thing is, if I run it again, with standard Visual Studio settings, well, now I have 4.35% in the same thing. So I have quite a high variance between run to run, and this is a problem. And this is a very simple example. In more complex code, when we have even faster function, we tend to miss function and stuff like that. So the accuracy is just not what we have, but well, that's a known sample limitation. All right, if we plug those same two functions into Ctrack, this is what we get. So the overall time is in this case, a bit over 2 seconds. We have then the variable timing function, which spends half of the time, roughly, and the micro-operation also. Well, great, that's exactly what we expect. Now let's look a bit more into detail in those two functions. Let's start with the upper table. The variable timing function has a very high CV, and of course. We call it 10 times with a wait for long and sometimes wait for slow, and that's why we can show it has a very high variance. The micro operation, on the other hand, is very stable, so it's 0.14 or something. In general, values above 1 means very high, and below that it's usually much more in the range of what you expect. And you can also reconfirm this with the table below that. So looking at the fastest events of our variance function, well, it was around 1 millisecond. That's what we would expect, right? Because we slept at least 1 millisecond in this function. If we look at the slowest event, well, we have a bit over 100 milliseconds. Well, that's exactly also what we would expect. And then in the middle, we have this, the median, which is still one of the fast, because we just take the middle element. But the mean or the average is much higher, because we have this very huge slow calls and some of the fast calls, so we have both here. All right, now let's talk about customization a bit, because this was a very basic workflow. How could we use it? But we want to customize it, right? So there's a couple of things we can do. We can do custom namings. Sometimes I want to name my function in a specific way, so you can adjust it and do that. Basically, just adjust the macro and yeah, you said. The next thing is going back to one of the first slides, talking about development and production. So we also have flags for development and production, and you can compile in such a way that on your development machine, you get everything or just the development flags or both. And on the production machine, the development tracks are disabled. So you have some sort of fine control over there, what do you actually want to track and what you don't want to track in production. Then we have the scoping. So what's quite neat, I'm going to explain in a second how it works, but Ctrack uses scoping to track a function. And for long functions, we might also add subscopes and track those parts of the program. So we can give them custom name. In our very complex algorithm, we have some initialization, and then we sleep there for a bit and track that with a specific Ctrack name. And then doing the actual iteration, we track this with a different name. So we can, especially in long functions where we interfere with different other stuff, it's quite nice to have that we can do those subscopes. Yeah, and there's more things we can do. As I said, we can adjust the range, what are the center events and what are the outliers I want to exclude. Also for us, it's really important, right? It's easy to use. So because if you track everything, you probably get a table woof, I don't know, 200 entries, even more. That's hard to use. So you have some options to exclude functions which did not at least take, for example, 1% of your runtime. Or you can set it to any value you want. Or you can also say, well, I want to exclude the fastest n% of my total function. So maybe I just want to have the 10% of the slowest functions overall. So you set that to 90 and you exclude the rest. And then we have different outputs, so you can directly access in code. That's the easiest. You can output, as I said, to terminal, to a CSV, to different files. You're pretty flexible on that. So before we do the deep dive how this all works internally, I want to show a quick real-world example which I just had 4 weeks ago. So we're working on one embedded project, working with 6 industrial cameras for measurement a specific item of the customer. So we had 3 2D cameras, 3 3D cameras, a lot of data going in and out. So when I was sitting there developing on my high-end dev machine, running WSL to use Cloud Code like everybody does nowadays. And yeah, well, I measured and I was very sad to see, well, grabbing frames takes like most of our time. So I wanted to things go faster, and I was thinking like, well, how can I optimize this? It's basically the camera, right? There's nothing I can do. And the segmentation, I'm just gonna highlight that because we need the next slide, is like super fast, it's no problem. But since I had like Ctrack installed, I could just run it on a production PC, like with one click, and see, well, how does the output differ? And there we have a different story. I expected the PC to be slower, for sure, because it's not as powerful as my development machine. But actually the frame grab was like way, way faster than on my machine. And that probably was due to some like firewall, WSL stuff. And yeah, just the package from the cameras were so much slower that, yeah, well, it really shifted my picture. That's like one of the use cases we have, right? Not just working on one machine, but also if you run your code on a different machine, you might get much different results. So it's really important like to measure as often as you can. So yeah, and that enabled us to work on the segmentation network, make it a bit faster, make it a bit more efficient, and like save a lot of the time on the actual production machine. All right, now we're gonna go into a bit of the implementation details, like how does Ctrack actually work? Starting very simple. This is basically what we record. So we record events. Events have a start and an end time, the location where the event happened, and which thread the event was, and also a thread-specific ID for each event. So Ctrack does use resource acquisition is initialization as a method basically, which is quite nice because with this like lifetime management of those Ctrack objects, we get basically a bit of best of two worlds. I'm sure most of you implemented, for example, lockguard or something, and instead of manually like locking and unlocking a mutex, and that's basically the same. So you have a bunch of like advantages doing it that way. Let's say we call Ctrack, then our macro expands to basically like this call, which then generates an object. And when we leave this function, this object already gets automatically gets destructed. So we can't. It doesn't matter if you like return early or if there's an exception shown or whatever. This object will always be deconstructed. So we will always get the result of this event. So that's quite nice. That means we just need to change like one line of code. So it's easy. It's exception safe. And also like Ctrack overall is designed with minimal overhead. That's the next thing we will show. Yeah, but first, it seems I forgot one slide. There are some advantages now, obviously, over like manual timing. So no need to like automatically write like multiple lines of code. It's much more cleaner, and yeah, and it's also fast. And the most important maybe, you get more insights, right? Because you get all those things I just showed, and not just like from one function, one output. So yeah, but now we are at this point where it's like, well, we record all sorts of that stuff and can produce all those metrics, but it should still be fast, right? So how do we do that in general? There's many tricks we use. I just picked out some of them because, well, the time is also limited here, sadly. So let's start with the first one. So we need some sort of like global storage where we put all our events, because doing our program, some threads might spawn, record some events, might die. So we need like some place at the end where we can collect all those events to then go loop through them and calculate everything we need. So, right. And then we need to design it in a way that the recording for each event on each thread is like not locking or blocking at all. So it needs to be as fast as possible. To achieve that, we have this event ID. Basically, once a thread, the first time a thread registers an event, it blocks a mutex, and that's like the only lock we have. I'm very sorry, but like spawning a thread, we need to wait a tiny bit of amount if we spawn them at the same time. Then we create this buffer where we will store all those events, the struct you just saw earlier. Register this buffer with our main storage, and already that's a small trick. Reserve quite a few items already, since like we want to save time. Because like let's say if we start with like a smaller vector, then it might like reallocate more often. But it's also like a trade-off. Just to take a quick side quest. We also played around with custom like growth strategies of those vectors and stuff like that. And of course, it's a trade-off. Like you need more memory. Like if you be more, you need more memory if you're being more conservative. and want to make sure it's very, very fast and a bit scared. And well, if you take less memory and allow more reallocation, your overhead gets a bit higher. So it's a bit of how to balance that. So yeah, and the neat part at the bottom is then when we record such an event, we can just in place construct it inside our result struct, and that's it. So no blocking, no checking. All the vectors can basically just fire as they want. So in a sense, each thread owns, not in a lifetime sense, but like has its own data structures. And only like doing the first event of a thread, we have this tiny bit of overhead, and then we have basically like a log-free hot path. So the recording for all threads happens without any synchronization. And that scales rather well. For example, on my laptop here, I can record around 75, 80 million events per second, which is quite nice. But also we have some more detailed benchmarks in the GitHub repo. All right, the next thing is, for those metrics like active exclusive, right? We somehow need to know child events of our events, else we want to exclude them. And how can we do it in a way that we take the least amount of performance calculation overhead, whatever, and still have this tracking. There we use a neat trick. Once a new event spawns, it first checks, well, the event before me in the same thread, was there any? And if so, give me your ID. So it remembers its parent's event. Then it does its stuff, it gets deconstructed at some point, and then it registers with the parent event as well. Here was an event, I was a child of you, and we set this ID. And what's quite nice, thinking about it, even if you have many of those events chained, the constructor is always guaranteed to resolve in the correct order. So there's never a problem. So you don't need to do any calculation or any explicit tracking or anything. Just by grabbing this ID at the start, and at the end I'm giving this back, we have this perfect relationship from a parent to the next child to next child. We have all those relations with basically nearly no overhead. So yeah, and that's what enables us for this time active exclusive metric, which for me itself, it's I think the most important one, because that's the one I'm using to find out what's slow, right? That's the idea. And yeah, and basically we get those again, this perfect relationship and have not to write any management codes to do that. All right, there's some more small tricks I would yeah, I think we have time. I would like to mention. So I said the result calculation can take some time, but I still want to be as fast as possible, right? Because at the end, I'm a developer and don't want to wait for my results. So during all this calculation, we have a couple of places where we use a execution policy. That's completely optional. You don't have to use it if your system or compiler doesn't support it, especially in the CppCon with some, they don't have it by default. But of course, you can use it, so that makes your result calculation faster. That's quite nice to have. Then another thing is that we have this interval merging thing. I think I mentioned earlier, let's imagine we have 4 events. In this case, it's 10 milliseconds, and they all start at the same time, right? Then we have 2 things we want to know. First, the accumulation. If I add all of them up together, well, we have 40 milliseconds, right? So I want to know that, that's fine. But from a top-down view, looking at the execution graph, basically, or execution flow of my program, well, only 10 seconds were at the same time spent in those functions. So that's the second metric I want. So we can also merge those intervals. And now we are slowly going more in the bit of the open source thing. So we also had to think about stuff well, how do we do it? If different people use Ctrack, maybe in a different version, stuff like that. So there are also techniques here, the version namespaces, where we make sure we have no ABI breaks when different people use different versions of Ctrack. So we also save here, which is quite nice to have. All right. And now I want to talk a bit about the adoption, the use cases, our experience with Ctrack, how did it went. Of course, as I said, first we basically built it for ourselves, right? It was we needed it, and so we built it. And then we thought, well, why not open source it? We're using so many open source libraries anyway, and that's the part we can really good make it. It's one package, right? It doesn't depend with anything. Why not open source it? So that's what we did. And yeah, it was quite nice. We got a couple hundred GitHub stars. It was used for contributions for ClickHouse, for example, this high-performance C++ database, which is one, if not the biggest, C++ project on GitHub. Of course, then for many of our own projects. Another thing, we are currently working on integrating that into the Hank AI darknet flow, which is the neural network in C++ for the YOLO detection, which would also be nice to have. And this is a very interesting thing, because this is sort of the worst scenario you have, like a neural network where you want to track like every operation in such a network that really puts it to the limit, right? So we are working on that. All right, so, but making it open source then also had some things which followed. First of all, there's now a commitment to maintenance. Like we as a company are now having to make sure we maintain the stuff and add more features and maintain it and all that stuff. And now also, sadly, there's a sort of responsibility because let's say I want to improve Ctrack, make it faster. I have to make sure I don't break the stuff for any other of my users. So that's why now we added some more things to Ctrack. It's already on a branch on GitHub, but will be released into the main branch somewhere next week. So we created like a benchmarking suite where we have like all these different types of calculating the overhead on different systems, like the precision against some known values, like how much the memory efficiency, like how much memory do we actually need to record those events, but also doing calculation, like how much memory do we need there. How does it scale, like running it on one core, like on many cores, on many machines, all sorts of that stuff. And we have like a baseline now, which before we release a new Ctrack version, we will run this and get like a baseline and we can compare all the metrics to the last version. So we can really make sure a new Ctrack version is not like slower than the last one, which is super important, of course. And but like speed is not all. You also need it to be correct, right? That's the second thing. So we have like a test suite where we use doc test. So this is our only dependency, but you only need that during development. I think doc test quite matches nicely to the philosophy of CMake, so that's why we chose that instead of a bigger framework. And we made different categories, like from basic tests, which are super easy, then for multi-threaded scenario, for nested, for statistic, also for recursion, which is like a super interesting thing you need to handle. Because if you exclude tiled graphs, you need to think about, well, how am I going to solve that, like if I call myself and still want to have like meaningful metrics, right? On all sorts of corner and edge cases. So we have like over 100 test cases and still want to like grow and extend them. And yeah, and want to make sure it just like works in every scenario, like even if you spawn like weird thread pools interacting with each other or whatever, so it just needs to work and be stable. So that's the second thing we now built. And yeah, and we also have a roadmap, like features we thought of ourselves, but also since it's on GitHub, we got cool ideas actually, like from the community. We got like feature requests, we got also some improvements, and that's really nice. And I think that's quite also a power of open source, because together we can make, together we all can make this better. So some things which are on our list right now is that it should be rather trivial to make like a flame graph export, which is then quite nice, and you can use it in our other tools. It's cool. We're also adding a JSON export. It's also very simple. We just didn't do it yet, so okay. Want to extend like the CI/CD runners on GitHub, so we don't have to do all the testing on our own infrastructure. We can just do it directly on GitHub and use Microsoft for that. Then there might also be a need where sometimes you don't want to use chrono or like a time point. You want like to use processor clocks. But thank God, like Ctrack is like very simple. It's just like two places where we calculate like the actual number. So it should be rather easy to switch that. But of course, we need to also make sure that then the analysis still applies to that. But that's something we want to have for sure. And talking about this neural network, maybe there's also a light version, because the recording of like 200 billion events, that worked. That was no problem. But then like doing all the analysis then on small machines like took some minutes, and it was like, well, maybe for this neural network, I don't want to have every metric. I want it to be a bit faster. So maybe we also will build a light version where we have like less metrics, but to be a bit faster. And of course, like we're also very open to your ideas. There might be tricks, and I'm sure there are tricks which you guys know are using, or metrics which you know like, oh, this is like super relevant. I'm looking at this and I can make my code faster. Yeah, we would like to have them as well. So feel free like to suggest it or anything. And yeah, that's why we are also very happy for contributions. Like submit your pull request. Of course, make sure like the CI pipelines then don't break and stuff like that. Feel free to report issues. We test on the main compilers and stuff, but there might still be some systems which behave a bit differently. So yeah, feel free to report those, or like any issues at all, of course. Then as I said, request features if you have cool ideas. Like another idea a guy had, which might be also cool, is that we have maybe a view like per thread. So we have this like, can choose like, well, I don't want to have the complete output. I know which thread is maybe the most important. So just give me the events of this thread, and I want to look at this data. And yeah, feel free to tackle the roadmap. Many of those features are rather trivial. So it's, I think, also a good way to maybe get started in open source, like without having to go like extensive, like huge pipelines. So it's many of those features are very easy and should be fast to merge. Perfect. And now usually is the time where we would do like the summary, right? In every slide, in every talk, you get like a summary slide and sum it all up. But specifically, I wanted to do something different. And now the next 2 slides, they are, for me, the most important slides, for sure. Maybe not the most professional, but for me, it's very, very important to go through those. Because, like, first of all, I want to thank, like, everybody of you, like the attendees, the speakers, the organizers, especially also the volunteers and the technicians to make everything possible here at Ctrack. So, yeah, big, big thanks for that. Then also I want to thank my colleagues and my team, like to challenge me in the ideas. Just with collaboration, such ideas and projects can exist. And last, but for sure not least, I also want to thank the people at home, the people who enable to do us those things. For me, specifically, it's my family and of course my wife. She has my back, she always supports me, and yeah, she enables me to focus on stuff like that, to follow my passion, and that would just not be possible without her. So thanks for that, Laura. And looking at all those people, that brings me to my final slide. And that's the most critical bottleneck I want to talk about. And if there's anything you remember from my talk at all, or from the many things you will remember from this conference, I would be very, very happy if this is one of the things. It's the ultimate bottleneck. And I will look at my notes a bit to make sure I'm not messed this up, because for me that's like super, super important. Because at the end of the day, like we spend our careers optimizing everything else, right? Our compilers, our algorithms, our pipelines, even the language itself we're working on. And often we forget that like the most complex system in the entire chain is not a constant. That's the human developer. So similar like to how software performance can vary, human performance varies like even more. Some days we are this 10x engineer we all want to be. Those are great. But other days we get stuck on a simple bug for hours and hours and can't make any progress. We get tired, we get burned out. We have things to do in our lives. And that's why I think it's fundamentally important that we look out for each other. Like, help your colleagues. Sometimes maybe just ask, hey, are you okay? That can change so much. And there's a crucial difference with a code bottleneck, because if one function is slow, it will track down the whole program all the time, right? You must, like, nothing you can do. But it's a bit different with humans, and we have a big luck in that. Because let's say on one day your colleague has a problem. Let's say he is the bottleneck. You have the chance to help him, like to offer help, share some of that load, support him, and that bottleneck might be gone faster than you would think. So in a sense, by optimizing this bottleneck, we can make huge progress. Because what's like super, super important is we can always replace code, right? We can basically replace any code we change. But we can't replace the human like sitting next to you, the people you work with, or any person at all. So I think for me, that's the most important message I want to talk, or I want to give you guys and really think about it. It's like still humans and try to help and collaborate to fix like this bottleneck also doing development. So thank you very much. And I still think we have some minutes for a question and answer.
Thank you for the nice talk. So what you have shown us is that I have to annotate every function where I want to get the metric.
Yes.
Have you already something like an automatic annotation of all the functions?
Yes, so what's quite interesting, if you look at Tracy, there was also Tracy Profiler also talk at CppCon. They do precisely that. They have like some clever compiler flag where they implement it everywhere. And we also thought about it, but did not yet do it, because in these LLM times, it became rather trivial to just say to your code agent, well, for every function, please enter the Ctrack, and that's it. I think I agree it would be nice to have, especially like for really, really big, huge code bases. But for us, it was, for now at least, too much effort to like think about all compilers, because then you need to be like really clever, like on each compiler, how do you do it? But for sure, it would be nice to have, just have like a global switch, like turn on Ctrack, everything is Ctrack. So for sure, that would be nice to have, but we didn't come around and do it yet.
Because that would also be less intrusive to the code base.
Yes, for sure. That's like one of the goals. So what you can do is that you can like disable all of Ctrack with one flag, like Ctrack disable, and then like pretty much like this macro gets mapped to nothing, so it like disappears in a binary. So you have that guarantee. But of course, in the source code, you still have this macro. So yeah.
Thank you very much.
Thanks.
Have you checked how it behaves with tail recursive functions?
With recursive or?
Tail recursive. So basically, when the compiler is able to transform a recursive function into a for loop, I guess if you add your check in this one, it's going to break because of the dependency to the call.
Like, I'm not sure about that, to be honest. Like, we obviously support normal recursive functions, so we handle that. But I have to check. I have to admit, I have to check. I don't know. But let's check on that.
Thank you for the talk. Did you check what is the overhead per entry? What is it?
Yes, so we have metrics also, like they're a bit more detailed on the GitHub, but it's in the nanosecond range. So it's like actually super low overhead, because that was one of the like key design decisions, and we also like made a lot of improvements over the versions and iterations. So really like in the nanosecond range on like fast computers.
If I take the same executable that is compiled with Ctrack, can I enable, disable entry point, or it is part of the code?
Yeah, sadly you can't do it on the fly. So yeah, right now it's like doing compilation. You need to decide where I want to have Ctrack enabled or not. Okay. Yeah.
Just as a reference,
Sure.
there is a project, open project for Morgan Stanley called Expedite. It's providing the ability to see all the trace point from on the executable and enable, disable them in runtime and see them changing the executable on the fly.
Well, that's what might be very nice to have, because then you don't need to carry those two versions anymore, right? So that's interesting. Yeah, I'm going to check that out for sure. Thank you.
Thank you.
Thank you for the talk. I have a couple of questions.
Sure.
One is, I'm coming from a proprietary part, and we use tools like telemetry and telemetry dashboards. And the question for me is, there's also, like I checked, open source project on what differentiates your tool from telemetry tools.
Well,
and
yeah.
The second question would be, you said like you have the capability to differentiate between dev branch and prod branch. Assume you have like A/B testing and you have different branches. Is it easy to basically manage this with your tool as well?
Okay, yeah, sure. Let's start with the first question. So it's a bit different than classic telemetry, since like Ctrack is really here focused on this high performance part, so that you have like basically no overhead, and it's not so much about like system health or general metrics like in a big system. So
not necessarily. So like the question is like, is telemetry giving more overhead, that much overhead? Because we used it in prod systems for fast applications.
I think so, yes. But then again, I don't have a benchmark to that, so I don't want to say anything wrong. So yeah, would be nice to find out, but there we don't have a comparison with that tool yet. But for the second question, I think that's easier. Like those dev and prod flags, they're basically just one line of code. So you can also like do your custom flags or whatever. So it should be like very easy to make like a collection of those and say, well, I don't want to run those in testing and those not and stuff like that. So that should be rather trivial.
Okay, thank you.
Thanks very much.
Okay, thank you. Very interesting. Could you clarify more about memory management? So I saw the part where you're pushing the events on. When do you take them off?
Yes.
I mean, if you just keep pushing it, well, at least in our code, it would be like a few gigabytes per second. Then what?
Exactly. So right now we are like recording this event, as you said, I explained correctly. And once you like calculate the results, you flush them. We are also thinking, that's one point of our roadmap, which I didn't mention, about sort of like a ring buffer, where we have like a limit of events to make sure that it doesn't happen if we like never print the events and just collect and collect. But generally, we right now at least expect the user to periodically like print the events or lock them somewhere away. So then you don't have this problem.
But the printing is what does all the calculation, accumulation, statistics, whatever
yes.
you do. So that's disruptive. That's fairly
Yes,
expensive.
but you also have an option to serialize like the data without the calculation. That's also in Ctrack. But of course, that also takes some time. So yeah. So basically, what we are doing with those situations, mostly in production, we don't want to track everything. So like, especially often we have like nested function or something. So we can get rid of like, let's say, I don't know, 70% of the Ctrack calls by not excluding, using like the smallest function. And what's quite nice, we can find the fastest and smallest functions by using Ctrack itself. So we can sort of like invert it. And yeah, also like often, at least in our programs, we have like some time where we have time like to stash the list or clear it. And you always have the option like to clear the memory. That's you always can do like without calculation, like discard all the elements, but probably it's not what you want.
So
exactly.
If you want to collect everything,
yes.
So you're relying basically the processing would flash, but it would also eat into the CPU time.
Yes.
Okay. Minor thing. I think you were storing file names and function names in strings.
String views.
Oh, they were string views. Okay.
String views, yes.
Okay, so there is a hit for memory allocation, right? Every time you push the.
Yes.
Well, every time the vector reallocates, so or you just pre-reserve them and you never reallocate.
Well, we pre-reserve them, but we have to sometimes reallocate. We did like test with a lot of different like data structures, like DQ and all sort of that stuff. But that's just for the inside loop. Let's maybe go back really quick. I can show it. So the global store is actually a DQ where we store those vectors per thread. So that never gets like the big object never gets reallocated. But
like if you're not starting many new threads, that's composed.
Yes,
stays.
yes, exactly. That was actually something we worried about like quite a lot and did a lot of benchmarking. But for us, it was still faster to use like a vector, make a bit more aggressive like growth strategy than STD default does. And yeah, that was basically our solution. But of course, you have some overhead there. The other options which you also checked in would be to like, check for this like location that already happened and like reference it. But like this lookup also adds overhead. So it's like you have to die this or this step. So yeah.
Okay, and the last question is like, let's say I have some functions that are basically, they're like worker functions. They only get called from other threads. Mm-hmm. So I have, but they can get called from any threads. Do you have a way to attribute their time to the correct parent thread?
Currently not, sadly. So that's one of the weaknesses. Right now, this active exclusive and child threads only works like in a thread. And we don't have like this linkage yet. Might be nice to add, but currently we don't have that.
Because I know how to do that, like if you're willing to be invasive on your source code, that's what
sure.
I have. But okay, you don't have that. So I was curious.
Not yet, but
there's a way to do it without like essentially passing the parameters through your entire
yeah,
code.
that's what we want to avoid. But feel free to like help us there. It would be nice.
Well, I know how to do it with passing parameters. So the call stack, I wanted to see if you can do it better.
Without it. Yeah, well, I don't think you can actually. Well, maybe you can, but at least we don't know how.
Okay. I don't know either. Okay, thank you.
Maybe someone here will help us out in the future.
Thank you. It was a privilege to be able to sit next to you last night at the dinner, so I wanted to thank you for that. And you may have answered part of my question, I think, just now. But all of the computation happens on the back end. You have this data that you go through, and then you do this accumulation after things are done. But if you want to watch something and you want to collect it on a long-running process, or even something that you're running live, how difficult would it be to say, you said you had some type of queue, but how difficult would it be to say to have that go across and have an external process doing it and doing all this processing in the back end, either storing it or doing live processing? One of the things that is important is evaluating something that's running in real time. Mm-hmm. And I have something like this, but as you said earlier, you guys are already committed to making sure that you support it and make your customers happy. I'd be glad to throw my thing away and just use yours.
Sure.
But how hard would it be to do something like that?
I don't think it should be too hard because like at the end, the event structs, they're very simple, right? Like just those few properties. And like sending them over somewhere else to process it, I don't think that should be, like you need to sort of have like a scheduling timing thing because what might be an issue, but I'm sure you'll find it out, figure out, is like why we're moving it away and still new events coming in, how we can manage that without like always checking like for a block or something to still keep the overhead as low as possible. But generally like loading off the calculation.
But I heard you say you're already putting them into a circular buffer, right?
No, that's one thing on our to-do list for this long running.
To-do list. Okay.
Yes,
right.
yes. To like prevent, let's say they run it and leave it running for like, I don't know, days. Currently, if we never like record or flush it, well, we collect the event, right? That's what Ctrack does. But a ring buffer would then solve it, and yeah.
Thank you.
Thanks.
Hi, wonderful work. I do the same like everybody here. I also had a Python script that you select the directory and deployed all the macro on all the function body. What I like to search. My question is, I saw the result on the terminal. What kind of sort do you give?
How do we sort the results?
Because if I run
Yes.
it on a project, it will be 1,000 of lines.
Of course, you can customize, but per default, it looks like this on the terminal. I'm just going to open it so we can go through it really quickly.
Can it be done by name?
No, yes, so you can customize it, but usually we like the main table, we order by the time active exclusive per default, so like the slowest functions are at the very top.
No, by name. I'm only interested in my model. I don't understand all
Yeah,
the
you can customize like the sort function any way you want.
And if you are keeping the thread ID, you're working on Linux, no?
So sorry?
You're working on Linux.
Both, like Linux and MVC, both.
How you handle signal, if it's coming signal in the middle, you take the thread ID that is hanging on it.
Could you repeat? I'm not quite sure I understand what you mean.
Signal in Linux.
We're not using the signaling in Linux.
If there's signal in Linux, it is riding on the thread that you let them work on it.
Okay, well, we still would like act as it would still be like the work inside this thread, so we would not handle it any differently. So yeah, I'm not 100% sure if I get your question totally, but yeah, that would be my answer.
You're handling the nesting of the function.
Yes. Okay. Now I think I know what you mean. Yeah. Well, but we're not doing this explicitly, right? We just always, from a parent, know what the child function is. That's like all we have, like this one ID which is linked, and like the whole resolution of this graph is at the end doing the calculation. Like during the events recording, we just check. Well, it's a new event. What was my parent event? We store this information, and that's it. And like the whole resolution of this calc graph is doing the calculation of the results.
Why are you using Q instead of an order map, etc.?
We tried different data structures and quite around like some performance with reallocation and stuff. For DQ, it was just quite nice that we have a guarantee that it will never be reallocated, right? So that's quite handy. And yeah, that's what we were
By an order map, you can use sort.
Yeah, we can but it's the thing. Like we prioritize the recording speed because from some data structure it would be easier later to sort them, of course, for sure. But the recording itself would be slower. And like our highest priorities have like as little as possible overhead in this doing recording, and that's why we.
An order map is very fast.
It's fast, but it's not as fast maybe as it's not fast enough for every use case.
But it gives you a lot of sort material.
Yes. Yeah, for sure. Like the sorting that we have to do manually, like later doing the result calculation, so that's slower. But that's the price we're willing to pay to get a little bit more extra performance during like the storage without any hashing and stuff like that.
Thank you very much.
Thank you very much. All right, I think my time is also over. Thank you guys.